Okay? What happened? I go to the right side. Remember that before? This point was here. Now, this point goes to left. Okay? I will go a little more bigger, I don't know, 30 meters. Look what happened with this point. Okay? This point is near to 3 meters. We put a little more. Okay. Okay? Now, if you look there, we are located exactly here. We are located exactly here. If we want to go to the next point, that is here, we need to add wavelength divided by 4 more. I mean, we need to add here more or less 12.5 millimeters. Now, our model remember that always you need to put millimeters. Then now we are near to this point. First we were in this point because the value was small. Now we go this distance and we go to this point. Let me change. Okay? Then if we look at here, if we go 13.5 millimeters, we are in the real impedance exactly in this point. If we add another 13.5 millimeters, we are in the real part, but in this point. If we add another 13.5 millimeters, we will stay once again in this point because you know the impedance is repeated each half by 2 wavelengths. Okay? Now, we have to choose what is a better solution. This solution or this solution, because in both cases we have as input impedance real part. Okay? We have two solutions. We have to choose what is the better one. This one or this one. Okay? How you select a solution? In this case, this position gives us a low impedance, and in this case, this position we have a high impedance. What is better? Okay? In terms of simulation, both are okay, but we have to analyze in terms of implementation. If we select this solution that is low value impedance, it means that the coupling of the impedance is a low value too. If we have a low impedance, it means that the impedance we put here has a wide width. Okay? If we choose a high impedance, it means that this impedance, say A, has a high value. If we have a high value, the width of the transmission line is small. What do you have to choose? This solution or this solution? Okay? What is the better? Okay? What do you have to choose? This solution or this solution? This one. Why? Now, okay, it depends. It depends on this size. For example, if we work, I don't know, in 8 gigahertz, the size of the antenna is small. I don't know. Let's give an example. What is it? Then we put the transmission line, and if we select the solution with low frequency, this will be the coupling system. And this width will be more or less 4.5 millimeters. Then here, these two structures are very similar. And because both are very similar, the antenna probably works with this patch and not with it. Okay, then there is a problem. If the size of the antenna here is bigger than this one, we don't take care about that. We choose the low impedance. In higher frequency, we have this problem. Okay? But what happens if we don't choose this, if we go a half factor longer, and here we do the coupling. The coupling is with small size. And normally, for example, this can be 1 millimeter. What is the problem we have here, 1 millimeter? Is the implementation. Because how you can get 1 millimeter of width? It's very complex. Okay? And it depends on the technology and depends on the frequency. Okay? We can do both here. Then, let's do this. For example, we are here in this position. We must be sure that the imaginary part is 0. Okay? We have to put this in 0. Then we have to go. We need to add a little more. We simulate. Okay? You see, there is nothing 0. We have to reduce. Okay, this must be exact value. Okay, for example, there. Then here, we have as a real part 183.41 ohms as an input impedance. We are in this position of the Smith chart. Okay? Now we need to make a coupling. Okay? Then, if you remember, we have here a calculator where we have here the coupling system. The lower impedance is exactly this one, 183.4 ohms. The frequency is 3 gigahertz and the input impedance that we need is 50 ohms. We calculate, and here the result gives us an input coupling impedance of 95.76 ohms. A width of the transmission line is 0.7934. And the length is 14.35 ohms. You go lock, you put the cursor, and you okay? Okay. Now, once we have this result with the real part any value, but imaginary part 0, we can make the coupling because we are exactly at the point that we need to stay. We go to the calculator, we go to input matching. In input matching, we put a lower impedance that is real one. We put a frequency that we work, the input impedance, and we calculate. And the solution is this one. Okay? Remember that this value, 95 ohms, the 95 ohms is exactly the result of the root square of the 883.4 ohms multiplied by 50. If we do this operation, the result will be this one. Because this is the equation for matching. Okay? Now, we need to add, okay, after this transmission line, the matching system, the coupling system. Then we need to eliminate the port. Okay? And we need to add here the transmission line with these elements. Okay? How we do that? Okay, we go to the footprint with port A and port B. Then we go here, we have the transmission line, and we need to add the transmission line for the matching system. Where we have here another width and another length. Then we go to the first point that is in the left side for you. It's minus $WA divided by 2 in X and minus $L divided by 2 minus $Y1. Not in Spanish anymore, in Spanish. Può darsi in italiano, ragazzi. Perché? Perché è bello l'italiano. Minus $LA. then the value of the width of the transmission line for matching system is 0.79, and the length of the matching system is 14.75 millimeters. Okay, then we have the point A and the point B of the transmission line. You can check it. Okay, guys. Then you can check this antenna with the coupling. This antenna is matching. We need to put the port once again here. And we need to simulate. What do we expect as a result? That the input impedance is 15 ohms. Then you can see here. This is 0 as imaginary part, and this is 50 as a real part. And the reflection coefficient is near to 50. Okay? That's the result, very nice result. Okay? Because you can see here that the impedance we have 0 and 50. Okay? Then conduit, look, this is the antenna, here is the impedance, this is the transmission line that we move it until to find real part impedance, and after we did a matching system with the transformer. Then we apply electromagnetic theory. Okay, electromagnetic theory is applied here. Okay? 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 Now, here you can put the feed. Okay? Then let's see. Okay? then this is what we did. Okay? This is the antenna, this is the transmission line, and this is the matching. Okay? And you see, this is how we put the connector. Okay? This is the connector, the signal, and here we have the reference. Here this antenna is with two polarization. Because if we put the antenna there, this is the linear polarization, vertical polarization with a fit here. But if we put a fit here, we have horizontal polarization. Okay? Then in this case, we can have two polarization, vertical and horizontal polarization. Okay? Now, we go to do the other simulation. I mean, we remove this and we need to go to the other solution. We eliminate the port. We eliminate this coupling. And we reduce this until put once again port excitation. And now we are not in the high frequency, we are in the low frequency with a value that is here 15 ohms. Okay? Then if we have 15 ohms, we go to the calculator, to the matching, now we put here 15 ohms, we calculate, and now the coupling is this one. We change this solution that is 3.6364 millimeters, and this length change to 34 millimeters. Now we eliminate the port and repeat what we did before, but with the other point. We put the other antenna.
Ya están suspendidos los cortes. No hay cortes.
But we need to change the dimension because now we have 3.5. And as you can see here, we have a real impedance near to 50 ohms. Okay? And there is not a good solution anyway, that's because of the time now. But here we have these two solutions. The first one is antenna, where we find a low value real impedance, and after we make coupling for 50 ohms. And the other solution that to go to a higher real frequency and to make coupling in the same way. Then there is two possibilities. For implementation, this is the best one, because if you can see, the sizes are normal. I mean, you have here 23 millimeters, 3 millimeters, 7 millimeters. That is not bad to implement. In the other case, what happened in the other case? The other case is longer, and after that there is a coupling that is very, very short. That was 0.79 millimeters. Then to implement 0.79 millimeters is very complex. Okay? So that's the reason for implementation, this is the better solution. Okay? Now, when we have the evaluation tomorrow, right.
Friday.
Then tomorrow we will continue doing simulations with the third possibility, that is insert fit.